Sirsi, and later on you will find out, Professor Usha Devi and Professor Ravi Shankar. Many of those contributions came from there. Professor Sirsi has been a regular, contributor to our activities all over India. I met her in Allahabad. I met her almost in all occasions. Whenever there's a workshop on quantum information, quantum computation. She was here in 2019, and this is the second time when she's here. But before she joins for a formal talk, I would like to tell you that apart from her academic and administrative and other kind of activities, she was a good cricket player. She represented the state and the college, if I believe, right? Yes. So it's a pleasure to introduce you to this young audience. And as you can see, slowly.
That was long back. I represented the South Zone in 1979. Yes.
My God.
Yes.
So you can slowly start because the students are going to come around. 400 regular students are around in Zoom platform, and apart from that, YouTube also people are watching. Okay. You can just slowly start in your talk, and people will join in.
Okay, sir. Thank you. It's Professor Panigrahi. It's always a pleasure to participate in QIQT. And 2 years back, I was in Kolkata, and it was you hosted a real good conference at that time, and unfortunately now it has become online. I hope after 2 years you will again host it in Kolkata, ISER Kolkata. So with this, once again thanking you. Let me start. I will. Can you hear me properly? Is the sound all right?
Yes, we can hear you properly. No problem. We can see you and hear you properly.
Okay, sir. Then let me share my slides. So let me start with this. So this is my topic. I chose this topic because I had to talk about measurement in quantum mechanics. And I believe most of the participants are students. So I thought I get an opportunity to talk about measurement to the students. And it's when I was a student, I found it to be very, very confusing, especially quantum measurement. So let me introduce the concept of measurement non-technically first and then technically. So let me start with the first slide. My topic is the joint measurability of qubit and qutrit operators. And my collaborators are Smita Rao, who is my PhD student, and another one is Dr. Karthik Bharat. He's from School of Mathematical Sciences, University of Nottingham, UK. And let us start. So this is the outline of my talk. I start with the introduction of measurement, and measurement is broadly divided into two kinds. One is projective measurement, and another one is some kind of generalized measurement called povms, positive operator value measures. And then I will introduce the concept of joint measurability, which you have studied in your quantum mechanics classes. And then I will go on to introduce optimum state determination, and then joint measurability of qutrit using povms, positive operator value measures. So this is the outline of my talk. And let me start with the introduction to measurement. So I thought I would share a very non-technical slide to begin with. We know the major difference between classical mechanics and quantum mechanics is in measurement. So I found this slide somewhere online, and I thought it is cute. So in classical measurement theory, your state remains the same. before measurement, it's a gray elephant, and even after measurement, it's still a gray elephant. So the outcome is deterministic. Whereas in the case of quantum mechanics, it's a superposition, as you all know. So it's the outcome, when you make a measurement on a quantum state, the outcome is probabilistic. Sometimes you get a colored elephant, sometimes you get a gray elephant. So I thought colored elephants are cute because I come from Mysore, and Mysore Dasara, you find many colored elephants. They paint the elephants with the different designs to make it very, very colorful. So it's a superposition of colored elephant and the gray elephant. And it can either be a colored elephant or a gray elephant. The outcome can be either one of the two. And another important difference between the classical and the quantum measurements is, in classical measurement, you can measure any variables, any variates simultaneously. For example, consider the height and weight of a person. At the same time, you can measure this girl's height as well as the weight. You can rig an apparatus which measures both simultaneously, precisely. Okay. And then, so simultaneous, there is a concept of simultaneous measurement, and thus there is a concept of joint probability distribution. So you can ask the question, what is the probability that given a person from an ensemble, her height is some h1 and her weight is w? You can ask that question. It's a perfectly valid question in classical mechanics. So let me start with the technical details. This you have studied again in your MSc classes. What do you measure in quantum mechanics? So it's quantum mechanics is usually taught with we teach the basic postulates of quantum mechanics. In fact, in my class, I start with the state postulate and how a state is a normalized vector in a Hilbert space. Then go on to describe the Hilbert space, state. What do you mean by normalization? What is the physical significance of normalization? And since Hilbert space is a linear vector space, it's endowed with an inner product. And what do you mean by inner product? And then you go on to describe the basis set which you can construct, which you can have in a Hilbert space because it's a linear vector space. And then go on to introduce this second postulate, which is about the physical observables, what you measure in an experiment. And we all know a physical observable is represented by a Hermitian operator in quantum mechanics. And then we go on to talk about the Hermitian operators and how Hermitian operators have real eigenvalues and eigenvectors belonging to the distinct eigenvalues form an orthonormal set, which can act as a basis for the Hilbert space, and so on and so forth. And we also, after this, we introduce, you have the state on one hand and you have the observables or the Hermitian operators on the other hand. So what do you do with them? You make a measurement. So what do you measure? This we introduce through the quantum measurement postulate. And the postulate tells you that the outcome of the measurement of an observable O of a quantum mechanical system in a particular state is given by the expectation value of the corresponding operator in that state. This you have heard and this you know very well. And the expectation value, quantum mechanical expectation value, is denoted by this. So you it's between you take the operator between a bra and a cat and you calculate this. And it's a real number because O is Hermitian. And this is for pure states. If instead of psi, if I have some general state psi, if I have an eigenstate, then what I get is an eigenvalue. These are all mathematical details which comes with the measurement postulate. Now, let me introduce the concept of projective measurement. This is the Swarnamala on projective measurements. So how do you introduce projective measurement? Again, mathematically. Given a Hermitian operator, you can, without loss of generality, you can take a finite dimensional Hilbert space, and the Hermitian operator is represented by some n by n matrix acting on the states of the Hilbert space. And since it's a Hermitian matrix, it can always be diagonalized by a unitary transformation. And this is known as the diagonalization procedure. You know what the procedure is, and you get eigenvalues and the eigenvectors. And any Hermitian operator can be written in terms of a spectral decomposition, which is given here. Okay, spectral decomposition, where Pi are the projection operators. This you can do to any Hermitian operator. And what do these projectors do? These projectors, they project any state into the eigenstates. For example, if I write Pi, just a second. If I write Pi as psi I, this is the projection operator, where psi I are the eigenvectors belonging to the eigenvalue Ai of the capital A. And therefore, if I make this Pi operate on any state, it projects the state onto the eigenstate. That's why it is called the projection operator. And these projection operators satisfy all these properties. For example, it is Hermitian, Pi dagger is Pi, and it's a positive semi-definite operator. Pi is greater than or equal to 0, and summation I Pi, it gives you the identity matrix, which is called the spectral resolution, resolution of identity. And Pi square is idempotent, that is Pi square is Pi. And if you take any two P's projection operators, then Pi Pj is equal to 0 for I not equal to j. Okay. I advise you to, or I ask you to play with these operators. So take any Pi, okay, and find this Pi tag. Find out what you get. You play around with these operators, then you will make sense of the following statements, okay? Next statement I'm making is, for the measurement performed on a quantum state rho, outcome AI occurs with the probability trace rho Pi. Because Pi is constructed from the eigenvectors belonging to the eigenvalue AI. Now I have introduced here an entity called rho. Okay. In the previous slide, I used only the pure state. In practice, we come across ensembles, statistical ensembles. So statistical ensembles are represented, they can not be, in principle, it is difficult to represent them in terms of pure states. They are, statistical ensembles can be considered as some N1 particles in psi1 state, N2 in psi2, etc., etc. And then you can give it a structure, okay? And you psi1, psi2, etc., or some vectors in some n-dimensional Hilbert space, and this N1 plus N2 plus etc. gives you a very large number of particles, say capital N, then you can identify that when you make a measurement, what you measure is the average expectation value of an operator O. If O is an operator, okay, these expectation, this bracket notation denotes the quantum mechanical expectation value, and this bar represents the classical expectation value. So if you have an ensemble of statistical ensemble of particles, okay, some of them, for example, if you are measuring their energies, then N1 particles have energy E1, N2, E2, etc. Then what you measure is the classical average of the quantum mechanical expectation values. And there usually that's the way rho is introduced. Rho is my state here, state of an ensemble. So it is, in general, we come across mixed states. So we proceed with the mixed states. And what is the post-measurement state? The post-measurement state is rho is an n by n Hermitian matrix. It is positive semi-definite, and its eigenvalues are the probabilities. Okay, and the probabilities, in the sense, you can think of them as the fractional populations distributed in the some n states. Okay, so if you make a measurement, PI, projective measurement on the density matrix, then what you observe or what you end up with is a final state density matrix rho F, which is given by PI rho PI divided by the small pi, which is nothing but the probability pi. So look at this. What is this probability referred to? Pi. It is the probability that you get in a measurement the eigenvalue AI. So this is the traditional way of introducing the projective measurement. Anyway, you are all familiar with this. I just, for the sake of completeness, I'm doing all this. And what is the importance of these projection operators or projective measurements? Projective measurements are repeatable because if you take, for example, a initial state to be some phi, and then you operate on phi with a projection operator PM, then PM of phi, PM operating on phi gives you a state phi m, right? And with the probability, therefore, if you want to get a state, then you have to divide it by the probability. And PM operating on phi m takes you to phi. So how many times you can take PM to the power of some n times, you will still be getting the same state phi m. And phi m is what? It is the eigenstate with which your PM is constructed. One important fact here is, even though we are talking about projection operators, not all projection operators are implementable. So it's usually when we teach quantum mechanics, we give the impression that all operators can be implemented physically and all projection operators can be implemented physically. It's not true. So next, if we think of, okay, when you make the measurement with a projection operator, then what you get is a sharp value. Because it's an eigenvalue, AI. So you get sharp value. If you have two or more observables, okay, then this also, joint sharp values can be assigned to commuting operators, because if the operators commute, then you can construct simultaneous eigenstates of 2 or more operators. And the moment you construct simultaneous eigenstates, you can think of joint short values, A taking the value some AI, B taking the value some BJ, etc., as long as A commutes with B. This is also a textbook problem. So, in the case of projective measurements, joint measurability, or this is called compatibility, it is linked to commutativity. If 2 or more operators are commuting, then they are set to form a compatible set, or you can perform joint measurement. They are jointly measurable. Now let us look at the generalized measurements. This we don't teach in your MSc, ordinary, regular MSc course. So one can introduce generalized measurements called positive operated value measures, POVMs. Okay. And these generalized measurements are associated with joint unsharp values. Or if you take a POVM, okay, and 2 POVMs, I mean, in a set you have some K POVMs, and then all these operators, positive operator valued measures, can be assigned joint unsharp values, because the values you measure are not, they are fuzzy. So they are called the joint unsharp values. It can be assigned to what kind of POVMs? It can be assigned to compatible POVMs. In the case of projective measurements, compatibility is associated with commutativity. In case of POVM, what is compatible? That is my next slide. So before going to the compatibility of POVMs, let us look at the mathematical definition of POVM. So don't be scared of this mathematical definition. It's not really very difficult when I introduce the POVMs in the case of qubits in terms of Polyspin matrices, which are very familiar. Here, I have to define it in a mathematical way. So a POVM, this is the definition for an index set I. A POVM is a set. Okay, it's a set, and which is given by this mi dagger of x into mi x, where I belongs to the capital I. And what are the properties of POVMs? These operators are Hermitian, they're positive semi-definite, and they also add up to identity. Why do they add up to identity? Because trace rho EIX gives you the probability. Okay, so X is called the measurement outcome. What is the probability that your measurement outcome is X? If I use a POVM, if I operate a POVM EI, then that quantity is given by trace rho EIX, as in the case of projective measurements. And here, in this case, the post-measurement state is given by this. See, since EIX is greater than or equal to 0, it can always be resolved into mi dagger, mi kind of operators, right? Because if you take any operator and if you take its Hermitian conjugate and multiply it, then you will get a positive, it's a positive semi-definite operator. So rho f is given by this, and the major difference between the projective measurement and the POVMs is POVMs are not repeatable. Projective measurements are repeatable. So let us I will define the joint measurability of POVMs. I said that you can define joint measurability to a compatible set of POVM. Excuse me. So what do you mean by joint measurability in the case of POVMs? In the case of projection operators, joint measurability was always associated with commutativity. In the case of POVMs, joint measurability is associated with a global POVM. How? I should be able to construct a global POVM such that the set E1, E2, etc., En, okay, should be obtainable as marginals of the global POVM. And when do you say G is a POVM? G is a POVM implies that it's a positive semi-definite operator, and it's a resolution of identity, etc., etc. It has to satisfy all the properties of POVM. So again, this is the mathematical definition. Okay. For example, if my set consists of E1, E2, etc., En, okay, then E1x1 is a marginal of the global POVM G of x1, x2, etc., xn. What do you mean by marginal? Look at the left-hand side. The measurement outcome is x1 here. Okay. So you have to sum over all the other outcomes, x2, etc., xn. Similarly, En xn you get by summing over x1, etc., xn minus 1. That's what marginals are. If you have studied probability theory, then you know the marginal probability, you know the concept of marginal probability and joint probabilities. And compatibility of POVM, as I said, does not require commutativity, but demands the existence of a global POVM and equivalently a joint probability distribution. So here, compatibility is not associated with commutativity of my POVMs. It is associated with a global POVM from which I can get all my marginals as my E1, E2, etc., En, marginals as that set. And when I say G exists, it means equivalently there exists a joint probability distribution. So this is very, very mathematical. We will find out about well, let's apply this to qubits. Then it becomes very clear. So let us look at the joint measurability of qubit POVMs. It's all very well known. And we know the Pauli operators, okay? Sigma 1, sigma 2, sigma 3. And the speciality of Pauli operators are all of them have the same eigenvalues, +1, -1. And you can write each and every Pauli operator in terms of its eigenvalues like this. Okay, this is the spectral decomposition. If you remember, x1, p1, x1. Similarly, for sigma 2, it is x2. But x1 takes values ±1, x2 takes values ±1, x3 takes values ±1. And how do you construct p1x? You construct p1x from the eigenstates of sigma 1. Right? There are two eigenstates belonging to two distinct eigenvalues ±1. So you construct P1 of x1 is something like x1, x1. Okay, outer product of the eigenvector belonging to the eigenvalue x1 is equal to +1. Similarly, your P2 is constructed out of the eigenvectors of sigma 2 and so is sigma 3. So the spectral decomposition is like this. And if you invert these equations, then you can write the projection operators in terms of the Polyspin matrices. Okay, so what is P1x1? It is this. Similarly, P2x2 in terms of sigma 2 and P3x3 in terms of sigma 3. Okay, there is a way of, so you know the projection operators, right? So the homework is you make sure or you find for yourself that these are the projection operators. How do you know these are the projection operators? They should be identified and they should be positive semi-definite. Okay, and if you take P1 and if you take P2, if you multiply them, you have to get 0. So these are the properties of projection operators. So do it for yourself and convince yourself that these are the projection operators. Now we know the povms are the unsharp versions of the projection operators. So how do we get the unsharp versions of the projection operators? Introduce a noise eta, or this is also called unsharpness parameter. Look at this. What is E1 of x1? X1 takes values plus or minus 1. Okay? And it's a combination of the projection operator, P1 of x1, which is also a pure state, and 1 minus eta times I2 by 2. You know, I2 by 2 is the maximally mixed state in the case of two-dimensional, in the case of a qubit or in the case of spin-half system. So how are you constructing the projection, unsharp versions of the projection operators or the povms? You can take the linear combination of the pure state and the maximally mixed state with a noise parameter eta. Then this eta varies between 0 and 1. Okay. If eta is equal to 0, what happens? Your E1 of x1 is the maximally mixed state. I mean, it's proportional to I2 by 2. Okay. And if your eta is 1, then E1 of x1 is the projection operator. So the povm goes to the projection operator when the unsharp parameter is 1 and goes to the maximally mixed state like I2 by 2 in the case of eta is equal to 0. And if you combine these two, then you can write this as this. Look at the P1 of expression for P1 of x1 and this expression. Here you have an extra eta here. Okay. Similarly, E2 of x2, povm, E3 of x3, another one. So you have constructed E1 with sigma 1. You can think of it as constructing E1 with sigma 1, E2 with sigma 2, and E3 with sigma 3. Now, this is, we are talking about the joint measurability of the povms. You can't jointly measure P1, P2, and P3 projections of associated with sigma x, sigma y, and sigma z. Sigma x, sigma y, sigma z don't commute. So, how do you associate joint measurability with these POVMs. As I said, you have to construct a global POVMG such that your E1, E2, E3 are the marginals of this global POVM. Okay. What is this global POVM and how do you construct this? It's given here, marginal POVMs. And since it's a global POVM, if you add all the G's, you have to get I. Okay. How many such G's are there? X1 takes 2 values, X2 takes 2 values, X3 takes 2 values. So 8 such G's are there. And each one of them has to be positive semi-definite. Look at this G. G of X1, X2, X3 is 1 over 8. I2, 2 by 2 identity, plus eta times some X dot sigma, or X1 sigma 1, X2 sigma 2, X3 sigma 3, where X1, X2, X3 are the eigenvalues of the Polyspin operator. And this G of X1, X2, X3 has to be positive semi-definite, right? Greater than or equal to 0. You can find for yourself that only when eta varies between 0 and 1 over root 3, this G is greater than or equal to 0. Otherwise, it is not. And this eta value, 1 over root 3, is called the robustness parameter, robustness value of eta. And we also know that trace rho G gives you the probability, joint probabilities. So I said, if G is greater than or equal to 0, then the joint probability distribution associated with G, then G ought to have a joint probability distribution. The joint probability distribution exists. So equivalently, a joint probability distribution P of X1, X2, X3 exists for eta between 0 and 1 over root 3. How do you find this joint probability distribution? You know that if I take trace rho G, I get the probability distribution. And we all know from our basic knowledge of quantum mechanics, okay, rho can be expanded in terms of Polyspin matrices in the case of qubits. So we will write it as something like sigma dot some more theta, where theta has components theta 1, theta 2, theta 3. And if I take trace rho G, I will get this probability distribution. So as again, I don't have time to show it, but you can all do it for yourself and find out trace rho G gives you this joint probability distribution. And for what value of eta, this distribution is positive. Otherwise, you can't call it a probability distribution, right? And the allowed values of eta is 0 and 1 over root 3. So this is about the qubit. This is about the joint measurability of qubit operators. Okay. Now the question is, it's always, if you consider a spin half system and a spin one system, spin half is your qubit and spin one is your qutrit. There is a sea of difference between the two. Okay. You can't just generalize whatever we know about spin half system to spin one system. And spin half system for all practical purposes is very well studied system. Its rho is very well known, and we have the block sphere representation of spin half. and we know what pure state means, what mixed state means in the case of a pure spin half, etc. But a qutrit or a spin 1 is a different ball game altogether. It shows you all the complications of the higher dimensional or qubits, how to handle the higher dimensional spins. Now, the question is, this is very well studied, as I said, joint measurability of qubit operators. Now, the question is, how do you find the joint measurability, or how do you extend this, generalize this to qutrits? Usually, the moment you say a three-dimensional system, you think of Gell-Mann matrices, the SU3 generators. Very well known, and they are constructed out of your, there's something like extension of sigmas. So, can we construct this global povmg using our Gell-Mann matrices? This question let us ask, and using the same methodology. Okay, so the moment I say the same methodology, then my G ought to be something like this. 1/3⁷ is for the normalization, because trace row G gives me the probability, and the sum, if I sum over the probabilities, I should get a 1. Okay. And I have this eta, and λ1, λ2, λ8 are my Gell-Mann bases, these U3 generators. Remember, what was the condition? I should get all my povms as marginals of this G. So, for example, if I want to get even λ1, okay, λ1 are the eigenvalues of the capital λ1, which is one of the basis matrices. Then, if I sum over all the eigenvalues, λ2, λ8 of this G, I get this E1 of λ1. And what was the other condition? The other condition was, if eta goes to 1, I have to get a pure state, pure projective measurement operator, projection operator. Here, if I put eta is equal to 0, eta is equal to 1, you don't get a projection operator. So, your even λ1 is not a combination of the maximally mixed state and a pure state. So you can't use the same methodology to obtain or to describe the joint measurability using these bases. So what should we do? We have to look for some Pauli-like operators. Okay. Pauli operators are very special operators, sigma i's. In higher dimensions, how do we construct Pauli-like operators? This is the question. For that, let us revisit the Pauli operators with a different perspective, with a measurement perspective. What is a measurement perspective? Let me go to a different problem altogether. The problem is optimum state determination. For example, if you have a qubit density matrix, then rho, as we know, is expanded in terms of, it has a spectral decomposition like this, and rho, since rho is equal to rho dagger, This implies that in n dimension, it has n square minus 1 independent real parameters. N is the dimensionality of the system, and this minus 1 is because of the fact that trace rho is equal to 1. There is a constraint because it's a state. So if I have the spectral decomposition of rho like this, then I can make n minus 1 independent. I can measure n minus 1 independent probabilities because the probabilities add up to 1, and there are two projection, n projection operators for an n-dimensional n by n density matrix. There are n projection operators of which n minus 1 are independent. So they yield n minus 1 independent probabilities. So I need at least n plus 1 measurements to determine all the n square minus 1 independent parameters. So if I optimum, because n plus 1 is the least number of measurements I can carry out to determine n square minus 1 independent parameter. Because in each measurement, I can measure n minus 1 probabilities. And this optimum measurement strategy involves what is known as mutually unbiased bases, or so-called MUBs. So definition, I will quickly go through this. What are mutually unbiased bases? If you are given two sets A and B, basis sets, then you take any one from this set and any one vector from this set and form an inner product. Then this modulus of this inner product, if it is equal to 1 over root D, then you say A and B form mutually unbiased bases. A has some, if D is the dimensionality, then A naught, etc. N basis vectors. These are orthogonal to each other. These are orthogonal to each other. This set, the vectors in this set and the unit vectors in this set are orthogonal to each other. But if you take any vector from the set A and any vector from set B and form an inner product and take the absolute value of this, I will get 1 over root D. So this is the definition of MUBs, mutually unbiased bases. And mutually unbiased bases are, if you make measurements in these mutually unbiased bases, then you can make the least number of measurements to get all the parameters of the state or the density matrix. That's why it is called the optimum state determination. Now, as I said, if in each measurement you can measure D minus 1 probabilities, so you need at least D plus 1 sets of MUBs to get the full information about the state. It is very well known. It's very well known that for prime and prime power dimensional Hilbert space D, there always exists D plus 1 sets of MUBs, and such sets are called complete sets of MUBs. Thus, for example, prime means if the Hilbert space is of dimension 2 or 3 or 2 to the power of 2, which is equal to 4, or 5, which is also a prime number. For all these spaces, a complete set of MUBs exists. You can construct them. Whereas if you consider the 6-dimensional case, 6 can be written as 2 into 3. It is not prime power. This is neither prime nor prime power dimension. So for 6 is equal to 2 by 3, it's still an open problem. How to construct? There are, we have only 3 sets of MUBs. How many sets do you need? For 6-dimensional case, T plus 1, 7 sets. So there are only, people have found out that there are 3 sets of, they can construct 3 sets of MUBs. This is called this is an open problem in MUB. So as I said, let us look at the Polyspin operators from the measurement perspective. So if I look at the Polyspin operators, observe these things. The observation is, if I take sigma 1, sigma 2, sigma 3, the eigenvectors of sigma 1, this set, these 3 eigenvectors sets form MUBs. Each set has 2 vectors, right? And these 3 sets form MUBs. That is, if you take any eigenstate of sigma 1 and any eigenstate of sigma 2 and call it as something like, if I consider sigma 1 as sigma x, then if I take some x1 with y1 and take the modulus, this is equal to 1 over rho. So sigma 1, sigma 2, sigma 3 is the eigenstates of these Polyspin operators are MUBs. So when you expand rho in terms of the famous expansion in terms of sigmas, and in Stern-Gerlach experiment, in order to determine rho, you have to make measurement using your magnetic field along the x direction, y direction, and z direction, right? Because you get the probabilities P1 associated with sigma 1, P2 associated with sigma 2, P3 associated with sigma 3, and these probabilities completely determine your spin-half system. So spin-half system is a 2 by 2 matrix. It's a 2-dimensional matrix. I mean, it's the states are 2-dimensional. It forms a 2-dimensional Hilbert space, and it has at most 3 sets of MUBs. And the 3 sets of MUBs are the eigensets of sigma 1, sigma 2, and sigma 3. So we have to look for operators with these properties. That is, I should be able to construct, okay, my operators, qutrit operators, which are like Pauli-like, using the MUBs. Okay, just a second. And I already showed you a slide in which sigma 1 is constructed out of the projection operators like this, right? -1 times P2. Similarly, sigma 2, the same form for sigma 2 also, except that I have P2 here, and P1 is constructed out of your eigenstate of sigma x, let us say. Similarly, P2, P1 of x1, okay. Similarly, P2 of y1 is constructed out of y1, y1. So, you can look upon this as, usually we take sigma z to be diagonal, right? So, sigma z, you can think of it as up and down. We have up and down states associated with the z direction. Then sigma z can be written as +1 times up and -1 plus of -1 times down. It is an outer product. So it is plus 1 times outer product of up and plus another eigenvalue minus 1 times the outer product of down state. Okay, now we have to look for same kind of operators in qutrits also. So how do we do that? MUBs are very well known in the case of three-dimensional systems, and it is this is a very famous paper by Bandyopadhyaya in which they give you the construction procedure for MUBs for prime and prime power dimensions, and let us not get into this. So the MUBs in the case of D is equal to 3, dimensionality 3 is first set you take it as the canonical basis 1 0 0 0 1 0 0 0 1. Then the second set would be something like this, okay, where omega is equal to e to the power of 2 pi I by 2. In other words, I pi. Okay. So these are the 4 sets of MUBs. Each set has 3 vectors because it is 3-dimensional. And if you take any one column here, and take an inner product of any other column of B2 prime, B3 prime, B4 prime, what do you get? The inner product gives you the absolute value of the inner product 1 over root D, which is 1 over root 3. So these are all very well known. So what we we constructed our operators, qutrit operators. So observe that sigma 1 is this, sigma 2 is this, sigma 3 is this. Okay. And as I said, one of them has to be constructed out of the canonical basis. So the projection operators out of the canonical basis. Similarly, if we look at the D is equal to 3, okay, I need 8 operators, right? Because n square operators together with I, of course, if I take the identity, then because we need orthonormal basis set, matrix basis, the inner product is defined through the Hilbert-Schmidt. And if I include I, then the rest of the 8 matrices should be traceless, and we demand that it is Hermitian also. So they form an orthonormal set. Okay. And my rho should be able, I should be able to expand rho in terms of this orthonormal basis set. And the parameters thetas are given by the expectation values of the alpha i's. For that, to construct that, we look for the diagonal matrix. See, if you take 8 matrices, Hermitian matrices, in 3 dimension, at least 2 of them are diagonal. Okay. So if you have diagonal matrices, then it is easy to identify the linear combination of the projection operators, because we consider the first basis set to be 1 0 0, 0 1 0, and 0 0 1, so that my projection operator P1 is something like 1 0 0 0 0 0 0 0 0. Similarly, P2, I have an 1 in the 2 2 place, etc. So we identify the diagonal matrices alpha 1, alpha 2 to be a linear combination in this sense. We also know that in the case of Polyspin matrices, all the Pauli matrices have the same form, right? Only thing is your P1 prime is P1 prime, P1 double prime, P1 triple prime are constructed out of their respective eigenvectors. Similarly, we construct alpha 3, alpha 4, alpha 5, alpha 6 out of the available projection operators which are constructed out of the MUBs. And this was published in Physica Scripta in 2019. And N1, N2 are the normalization factors. So people use different normalization. We use some normalization. And if you consider these sets, alpha 1, alpha 2 commute, alpha 3 commutes with alpha 4, alpha 5 with alpha 6, alpha 7 with alpha 8. So we have 8 operators, but 4 sets of commuting operators. Each set consists of 2 operators, and the eigenvectors of these sets, they form the MUBs naturally because we are constructing them out of P1s, P1 primes, etc. So these are all the exactly similar properties of the Polyspin matrices. Using these alpha 1s, okay, I have given the alpha 1s in next in detail. And how do we construct the projection operators and the POVMs? Projection operators are given by alpha 1 and alpha 2 now because I have 2 commuting operators, and P2 is given in terms of alpha 3, alpha 4, similarly this. And each x1, y1, they take values like this. X2, y2, similar. Similarly, in the case of Pauli, right? In the case of Pauli, sigma 1, sigma 2, sigma 3, all of them have the same eigenvalues. Similarly, here alphas, alpha 1, alpha 2, they don't have the similar eigenvalues, but this whole set have the similar eigenvalues. Okay, x1 times alpha 1, y1 times alpha 2. These are the eigenvalues. These are the simultaneous eigenvalues because alpha 1 commutes with alpha 2 and 3 with 4, 5 with 6, etc. Now, given these operators, I can construct our unshort POVMs as in the case of spin half. So these unshort POVMs are this, and we looked at the, as usual, eta lies between 0 and 1. And what are the global POVMs? Because once we have E's, there should be the marginal of the global POVMs. And the global POVMs, G of Z1. What is Z1? Z1 takes values x1, y1, and each x1, y1, there are 3 such sets. So there are 81 combinations, and it's a linear combination of alpha 1, alpha 2, etc., alpha 8, as in the case of spin half. And since trace rho G has to be positive semi-definite, and trace rho G has to give me a joint probability distribution of all these operators, eta can take value between 0 and 1 by 4. And this eta is equal to 1 by 4 is called the noise robustness. Only between these values of this unsharpness parameter, we can construct a global POVM. And the corresponding probability distribution looks like this, where theta 1, theta 2 are the expectation values. Trace rho alpha I is my theta I. And rho can be, as I said, written in terms of theta alpha i's. As in the case of spin half, a spin 1 system can be written as third. And this is the 3-dimensional unit matrix. And I have alpha dotted with theta, where alpha comes in 8 varieties and theta is an 8-dimensional vector. So if I apply this, then the joint probability distribution is this, provided my eta lies between 0 and 1 by 4. So now, what is the recipe for constructing Pauli-like operators? This you can study this. Similarly, I can do it for D is equal to 4. Okay, and in the case of D is equal to 4. That is equivalent to spin 3 by 2 system. Okay, then 4-dimensional qutrit. Okay, what is it called? Foldit. Okay. Then here I can construct a global POVM for eta between 0 and 0.2171, and the noise robustness is gone decreasing, right? In the case of spin half, it was 1/√3. In the case of spin 1 or the qutrit, it was 0.25. And in the case of four-dimensional object, it is 0.2171. And as we construct our operators using the MUBs, this procedure can be applied for prime and prime power dimensions where the MUBs are known to exist. So the problem was so far looking at the joint measurability of the generalized measurement operators. Why do we need it? Because in quantum information, we need non-classical states. And when you say joint measurability, then it is associated with non-classicality. Joint measurability is associated with classicality rather. And if there is no joint measurability, then it signifies non-classicality. And we need non-classical states for quantum computational tasks in quantum information and quantum computation. So we know how to do it, how to define joint measurability in the case of prime and prime power dimensions, because we can construct Pauli-like operators. So this is what we have done, and thank you very much for listening to me patiently.
Thank you, Swarnamala. Very, very nice, very clean talk. And I at least understood all of it quite nicely. Thank you. Now, questions, please.
Thank you, sir. You are always very kind.
Saran, you can read some questions if they are there.
Yeah, there is one question in the chat box. What constitutes a measurement which apparently causes the wave function to collapse into a definite state?
It is a projective measurement. It is a projective measurement, yes. Because when you take some kind of a PI and make it operate on some general state psi, then it collapses into phi I, right? Pi is made up of phi I. So it's a projective measurement, definitely. These POVM measurements are not this clean.
I have a question.
Yes.
See this, if I look at the Werner state,
yes.
Which is, identity plus some parameter and the,
singlet.
Doesn't it look like this measurement basis?
No.
No, for example,
it's I think if I remember correctly, Werner state is a linear combination of identity plus singlet state, right?
No, plus singlet state, right? Singlet,
yeah,
one
singlet state. Here, it's a linear combination of two density matrices. One is pure density matrix, and which is, pure, and the other one is maximally mixed density matrix with eta as the parameter.
Oh, okay. And then, for example, this pseudo-pure states in NMR, do they look similar? No.
I'm not too I know what pseudo states are in NMR, but I'm not too familiar with the algebra of them. I haven't looked into it. Right.
So what is the problem with, like, for example, dimension 6? What is the problem there? MOU will be difficult to find.
There are some papers which tell us that there don't exist a complete set of MUBs for dimension 6. It's a conjecture, not been proved. So even if you discover the 4th MUB, it will be published in physical review letters.
I see.
So it's there are only 3 sets of MUBs. For example, the next dimension occurs at 10, 5 into 2. Because, after 6, I have 7, which is a prime number. 8 is 2 to the power of 3. 9 is 3 square. Whereas 10 is again 5 into 2. So, thanks to Professor Bandyopadhyaya, we know how to construct for prime and prime power dimension. There also this non-existence of MUBs are also associated, the so-called non-existence, with so many different issues. For example, with group theory, they have an argument from group theoretical aspect also, that there can't be a complete set of MUBs in the 6th dimension. So, really, nobody knows whether they exist or not. If they exist, how to find them?
Okay. Are there more questions? If not, let us thank Professor Sirsi for a very nice talk, very clean, and hopefully in future we will also bank upon you. Thank you.
Thank you. Thank you very much. Thank you.
Good night.